Watch this video in Lesson Reach. Pause and ask questions, take a quiz, or get help with assignments. Link below.
I want you to do something for me. Like wherever you are right now, assuming you aren't, holding a steering wheel, I want you to look down at your hands.
Let's take a good look at your fingers.
Yeah, exactly. Look at your fingers. 10 fingers. I mean, it's a biological reality for, well, most of us. And because we have those 10 fingers, we have this deeply ingrained belief that the way we count, the way we do math, like our entire base 10 number system is just a fundamental law of the universe.
Right, like gravity or the speed of light.
Exactly. We think counting by tens is just the way the fabric of reality works. But what if I told you that it's actually just a massive biological coincidence?
It's a complete anatomical accident.
Yeah.
I mean, we take it entirely for granted, but our whole mathematical framework, the way we measure literally everything in the world, is essentially based on the fact that early hominins just happen to have 10 digits on their upper limbs.
Which is wild to think about. And that realization is honestly the perfect hook for what we are doing today, because we're going to completely deconstruct how humanity counts.
Oh, I'm very excited for this.
And to tackle this, we are leaning into a specific dynamic for this deep dive. I am going to plant myself at a desk and play the role of the curious student today. And you are going to stand up at the chalkboard, put your lecturer hat on, and just guide all of us through the material.
I am more than happy to take on the lecturer role for this one.
Yeah.
The material we have today is incredibly rich, and my primary goal, my mission here, is to completely shatter your reliance on base 10.
Consider my mind an open notebook then. So as the student, let me formally introduce the curriculum. Today we are exploring section 4.3 of chapter 4 from Contemporary Mathematics.
A fantastic section.
It really is. Our mission is to look at the bizarre, brilliant number systems used by other cultures and by modern computers and learn how to translate between them. So, lecturer, where do we start shattering illusions?
Well, we start with a pretty harsh mathematical truth, which is that base 10 is actually a rather awkward system. Yeah, it's really not an optimal way to group things in the real world. I mean, think about the number 10 itself. It only has two natural number divisors, which are 2 and 5.
Okay, meaning you can only cleanly divide 10 items into like 2 groups of 5 or 5 groups of 2?
Exactly. Now, picture yourself in an ancient market or, even just baking in your kitchen today. If you need to divide 10 items into thirds or quarters...
Oh, the math gets terrible.
Right. The system completely falls apart. You immediately get messy fractions and decimals. It makes everyday tasks like dividing up trade goods or packaging items surprisingly cumbersome.
But, I mean, if it's so clunky, why did it conquer the globe? Because if you travel almost anywhere today, base 10 is the universal language. It feels like, I don't know, if there were a better alternative, human efficiency would have just naturally adopted it by now.
Well, you'd think so.
Yeah.
But history doesn't always run on mathematical efficiency. It mostly runs on power. The Hindu-Arabic system developed base 10, sure, but its absolute global entrenchment has a ton to do with politics. Think about Napoleon's France.
Oh, really? Napoleon?
Yeah.
Huh.
During their era of aggressive expansion, they standardized the base 10 system, and the metric system, by the way, across their entire empire. So it spread through conquest, administrative control, global trade, not necessarily because it was the ultimate mathematically superior choice.
So we are essentially locked into an awkward counting system because of French imperial bureaucracy.
Pretty much.
That is wildly frustrating. But section 4.3 points out that mathematicians have long argued for a superior alternative, right? There is this entire organization called the Dozenal Society that actively campaigns for humanity to switch to base 12. So why 12?
Because 12 solves the exact problem 10 creates. It's a beautifully divisible number.
Okay.
You can divide 12 evenly by 2, 3, 4, and 6. I mean, a third of 12 is a clean 4. A quarter of 12 is a clean 3. If you are dealing with physical objects in the real world, grouping them by 12s is just infinitely more flexible.
That makes logical sense, but it sounds like kind of a utopian math dream. Do real, breathing human beings actually use base 12, or is this just something academics argue about in, like, obscure newsletters?
Oh, no, it is very real. The textbook highlights a dialect of the Gwandara language in Nigeria, and they utilize a base 12 system to this day.
Wow.
And even in our own modern, heavily standardized lives, the ghosts of base 12 are absolutely everywhere, particularly in Europe.
Like how we measure time, right? A clock face is 12 hours.
Yes. Or how we buy eggs by the dozen.
Oh, true.
Or how bulk goods are sold by the gross, which is simply a dozen.
Yeah.
We instinctively fall back on base 12 when we need practical physical divisions. But the most compelling evidence of how deeply this system was once ingrained is actually hidden right in our language.
The etymology, yes, this was my absolute favorite part of the reading.
It's fascinating, isn't it?
It's so cool. So think about how we count in English once we get past 10. We say 13, 14, 15. It's a very clear pattern, right? 3 and 10, 4 and 10, 5 and 10. But 11 and 12 completely ignore that pattern. Like if they followed the rules, they would be 1-teen and 12-teen.
Exactly. And they break the pattern because they are ancient linguistic hangovers from a time when counting didn't revolve around 10. The words 11 and 12 trace directly back to the Old English words einlif and twatlif.
And the textbook explains that lif is the root word for to live. So in live literally translates to 1 left over after 10.
Yep.
And twatlif means 2 left over after 10.
It's literally a linguistic fossil. The language itself had to create special standalone words for 11 and 12 because those quantities were incredibly important for daily commerce and life. And they carry all this baggage of an older, dozen-based way of thinking.
Okay, you have successfully broken my allegiance to base 10. I'm sold. But moving from theory to practice, if we were to adopt a different system, how does that mechanically work, like day to day?
Okay, let's run a thought experiment to visualize the mechanics. Imagine human beings had evolved differently. Imagine we only had 6 fingers in total, so 3 on each hand. If our biology dictated our math, we would naturally develop a base 6 system.
Okay, so in base 6, the very first thing that has to change is the symbols we use.
Right.
Because in our normal base 10 world, we have 10 distinct digits, 0 through 9. But in base 6, we would only be allowed to use 6 symbols, which are 0, 1, 2, 3, 4, and 5.
Which means there's no standalone symbol for the quantity of 6.
Right. And this is where my brain initially started to short circuit. Like, how do you write down the number 6 if the number 6 doesn't physically exist?
It's a trippy concept.
To wrap my head around it, I came up with an analogy. You tell me if this tracks with the math. I pictured a mechanical odometer in a car, but it's a base 6 odometer.
Okay, I like this.
So the dial rolls up, 0, 1, 2, 3, 4, 5, and then it physically runs out of numbers. It hits a wall. So the dial has to reset back to 0, and that physical rotation clicks the gear to its left up by 1. So the readout suddenly says 1, 0.
That is an excellent way to visualize it. When you run out of symbols, you shift to the next place value. But as a student, you have to realize that the 1, 0 on your base 6 odometer does not mean the quantity of 10.
Right, it means one group of 6 and 0 ones left over.
Correct. See, in base 10, our place values are powers of 10. We have the ones place, the tens place, the hundreds place. But in base 6, your place values are powers of 6. Moving from right to left, you have the ones place, the sixes place, the 36s place, and the 216s place.
Okay, so instead of organizing quantities into boxes that hold 10 items or 100 items, we are organizing the exact same amount of stuff into boxes that hold 6 items or 36 items.
Exactly. It's just a different container system. It's the same amount of stuff. Now let's stretch your odometer analogy a bit. What happens if the base is larger than 10? Say we are looking at base 14.
Well, the odometer dial now has 14 slots before it resets. But the problem is, our Arabic numeral system only gave us symbols for 0 through 9. We are literally missing 4 symbols to fill out the dial.
So how does section 4.3 solve the missing symbol problem?
We borrow from the alphabet.
Yes, we do.
We use capital letters to fill in the gaps. So A represents the value of 10, B represents 11, C is 12, and D is 13, which means a base 14 number might look completely alien on paper. I mean, it might look like a Wi-Fi password. You could have a number written as 4B7.
It looks alien, for sure, but the underlying logic remains perfectly intact. And the textbook provides a great example of this by taking a weird-looking number like 3024 in base 6 and converting it back into our familiar base 10 to prove the math works.
And we can do this without getting bogged down in tedious calculations, right? We just look at the boxes.
Exactly.
Yeah.
Just unpack the boxes.
Okay, so we have the base 6, number 3024. The 4 is in the smallest box, the ones place. The 2 is in the next box up, the sixes place. The 0 is in the 36s box. And that 3 is in the largest box, the 216s place.
So to find out how much stuff you actually have in base 10 terms, you just unpack them. You have 3 boxes that each hold 216 items. You have 0 boxes of 36. You have 2 boxes of 6. And you have 4 loose items.
Got it. And if you dump all those items out onto the floor and just count them up the normal way, you get 664. So 3024 in base 6 and 664 in base 10 are exactly the same quantity. They're just wearing different structural outfits.
Different structural outfits. That is the fundamental secret of number systems. But it raises a deeper question. How did different human cultures end up wearing different mathematical outfits?
Yeah, that's what I find so fascinating about this. Math isn't this universal monolith. It's an economic and cultural tool that evolves to solve very specific local problems. The textbook walks through a few historical examples that really prove this. Like, look at the Babylonians in ancient Mesopotamia.
Hi.
They used base 60.
V60. I mean, just think about that. That requires 60 distinct symbols before you shift to your next place value. It sounds chaotic, but it is actually a stroke of genius for an ancient civilization.
Because of the divisibility, right, like we talked about with the 12.
Entirely. The number 60 is highly composite. It can be divided evenly by 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30.
Oh.
Yeah, so if you are an ancient trader or an early astronomer mapping the stars without the benefit of modern decimal points, avoiding fractions is absolutely vital.
That makes total sense.
Base 60 allowed them to do incredibly complex calculations smoothly, and their mathematical architecture was so robust that we are still trapped inside it today.
That's the mind-bending part. The ghost of Babylon is ticking on our wrists right now. It is the reason we have 60 seconds in a minute, 60 minutes in an hour, and 360 degrees in a circle. Like, they essentially hard-coded the measurement of time and space for all of humanity.
They really did. But while the Babylonians optimized for mathematical utility, other cultures optimized for biology. The Mayans, for instance, they utilized a base 20 system.
Base 20, which I guess seems like a very natural conclusion if you are counting both your fingers and your toes.
It is deeply biological. And rather than memorizing 20 distinct arbitrary squiggles, they developed an elegant additive visual system within that base 20 structure.
Right, the symbols.
Yeah, they used a shell shape to represent 0. A single dot represented 1, and a horizontal bar represented 5.
So if a Mayan scribe wanted to write the number 7, they didn't need a unique symbol for 7. They just drew one horizontal bar to represent 5 and stacked 2 dots on top of it for the extra 2. It's incredibly intuitive. But then you look at early Hawaiian culture, and things get really interesting because they actually blended systems together based on their physical environment.
Yes, the early Hawaiians utilized a unique combination of base 4 and base 10. And as you noted, this wasn't arbitrary. It was born out of the physical reality of moving resources in their specific economy.
Right. The textbook explains that they grouped objects, say, fish or coconuts, into 4s. A collection of 4 was called a kauna, and that makes perfect physical sense. If you are grabbing fish out of a net, grabbing 2 in each hand makes a set of 4.
It fits the hands perfectly. 4 is a natural human grip.
But a base 4 system alone is terrible for counting massive quantities, right? Your numbers would get infinitely long very quickly.
They would. So they used a base 10 multiplier to scale those groups up. 10 of those kaunaso, 10 groups of 4, which is 40 items, was called a ka'au.
Okay, and then 10 ka'au, which is 10 groups of 40 or 400 items, made a lau.
You've got it.
So they retained the physical convenience of counting by 4s, but they bolted on the mathematical scaling power of 10s. It is just a brilliant example of how human cultures engineer math to fit their precise environmental needs.
Which brings us to the most vital alternative number system in human history, one that isn't ancient at all. It is the absolute bedrock of the modern world.
Base 2. Binary, the language of computers.
Exactly. Computers use base 2 because it is the ultimate physical restriction. An electrical wire really only has 2 reliable states. It either has voltage or it doesn't.
The switch is either on or it is off.
Yep. So the math perfectly matches the physical circuitry. Off is 0. On is 1. That is your entire alphabet. But there is a massive drawback to having an alphabet with only 2 letters.
The numbers become catastrophically long.
Very quickly, yes.
Because you only have 2 symbols, your odometer resets constantly. You shift place values almost immediately. So to express the number 100 in our base 10 system requires 3 digits, but in base 2, 100 is written as 1100100.
It takes 7 digits just to express a relatively small quantity.
Which is perfectly fine for a silicon chip processing billions of those 1s and 0s every second, but it is unreadable for a human being. Which brings me to a practical problem for you, lecturer.
All right, lay it on me.
If computers speak base 2 and we speak base 10, how do we build the bridge? We discussed how to unpack boxes to go from a strange base back to base 10, but how do we go the other way? How do we take a normal base 10 number and force it into base 2 or base 6?
Okay, so going to base 10 was about multiplying and unpacking. Going from base 10 requires a mathematical tool called repeated division. You essentially strip the base 10 number down for parts.
Walk me through the mechanics of that. I'm a visual learner.
Sure. You take your base 10 number, your dividend, and you divide it by your target base. So if you're converting to base 6, you divide by 6. When you do that division, you ignore the decimals and focus entirely on the remainder. You write that remainder down.
Okay, so the remainder is like the loose change left over.
Exactly. Then you take the answer you get, the quotient, and you divide it by 6 again. You write down the new remainder. You keep taking the new quotient and dividing it by the base over and over again, harvesting those remainders each time.
Okay, but until when? When does the loop stop?
You stop when your quotient finally hits 0, when the base can no longer divide into the number at all.
So now I just have a vertical list of remainders sitting on my notepad.
Right, and those remainders are the digits of your new number in the new base.
Oh, wow.
But there's a crucial catch. You have to read them in reverse order. The very last remainder you found becomes the first digit on the far left. The very first remainder you found becomes the last digit on the right.
Oh, that is clever. It's like breaking down a massive Lego castle, which is your base 10 number, by repeatedly snapping off chunks that are exactly the size of your new base. And the loose bricks that fall off at every single step, the remainders, actually serve as the blueprint to build the new number from the ground up, starting from the last piece.
That is a wonderful conceptualization.
Yeah.
Yes, the remainders are the blueprint.
But practically speaking, with all that dividing and harvesting remainders and remembering to read the blueprint backward,
There's a lot to keep track of.
right, there is a lot of room for human error. So if I am sifting this number through the filter over and over, how do I quality control my math?
Good question.
Mm-hmm.
Section 4.3 provides 2 highly reliable error detection rules for exactly this reason. The first is checking for illegal symbols.
Okay, because the digits of your new number are entirely generated by the remainders you got from dividing.
Correct. If you are dividing any number by, let's say, 4, the fundamental rules of division dictate that your remainder can only ever be 0, 1, 2, or 3. You can never divide by 4 and get a remainder of 4.
Because if you had a remainder of 4, the filter didn't work right. You could have just divided it one more time.
Exactly. Therefore, in a base 4 system, the symbols 4, 5, 6, and so on are physically impossible. They are illegal symbols. So if you convert a number to base 4 and your final answer is written as 3702, you don't even need to recheck your math to know you failed. The presence of that 7 proves you made a division error somewhere. It literally cannot exist.
That's a brilliant quick check. I like that. What is the second rule?
It's the digit length rule. This is about logical scale, and it revolves around an inverse relationship. Let's say you are converting from a higher base down to a lower base, like from base 10 down to base 3.
Okay, base 3 only has 0, 1, and 2, so the odometer is tiny.
Right. Because the odometer is tiny, because you have fewer symbols to work with, it requires more physical digits to express the exact same quantity. It is like using smaller buckets to carry the same amount of water. You are going to need a lot more buckets.
That makes sense.
So when converting to a lower base, the new number must have more digits, or at minimum the exact same amount. It can never get shorter.
So if I take a 4-digit base 10 number and convert it into base 3 and my answer only has 3 digits, I absolutely botched the translation.
100% botched it. And the inverse is true. If you move to a higher base, say from base 10 up to base 14, you now have larger buckets. You have more symbols, including those letters A, B, C, and D we talked about. Because each symbol packs more meaning, the total number of digits will usually decrease or stay the same. It cannot magically increase.
Okay, so higher base equals fewer digits, lower base equals more digits. It's entirely about the size of the container.
Nailed it. If you monitor for illegal symbols and you watch your digit length, you can spot the vast majority of structural mistakes in any base conversion.
Okay, I am going to drop the student persona entirely for a moment to just talk directly to you, the listener. Taking this deep dive into the textbook, stepping back and looking at the mechanics of counting it, completely shifts how you see the world around you.
It really does.
Numbers are not these cold, fixed laws of physics floating in a void somewhere. They are living cultural languages. They are human inventions shaped by our anatomy, by the fish we carry in our hands, by the stars we map, and by the electrical limits of the computer circuits we build.
It is a profound realization, honestly. And once you understand that base 10 is merely one dialect among many a biological coincidence that was kind of forced into global standardization, you stop taking the systems around you for granted. It hones your critical thinking. You start to always ask, why was this system built this way?
Exactly. It makes you realize that the way we do things right now isn't necessarily the ultimate truth. It's just the current iteration.
Building on that perspective, I want to leave the listener with a final thought to ponder. A sort of scenario that takes everything we've discussed today to its logical conclusion.
I love these. Give us the final thought.
Well, we established that humanity's dominant base 10 system is largely an accident of having 10 fingers, right?
Yeah.
But we also know that our most advanced technology, the servers that store our entire history, art, and science, run entirely on base 2. The digital bedrock of humanity is written purely in zeros and ones.
The ultimate base 2 archive.
Exactly. So imagine a far future alien civilization arriving on Earth long after we are gone. They manage to unearth our server farms and decipher our digital records. They translate the basic logic and realize our entire recorded civilization is built on base 2.
Oh, man.
If they didn't have a physical human skeleton to examine, would they assume humanity only had 2 fingers? Would they completely miss the biological reality of the creatures who built those machines simply because they misunderstood the mathematical language we used to speak to them?
Wow. That brings the entire concept home perfectly. We build these incredibly complex systems that eventually outgrow the biology that birthed them. It makes you wonder what else we are leaving behind that might be completely misinterpreted. Next time you look down at your hands, just remember those 10 fingers aren't just digits. They're writing a very specific, highly biased history of the world.